So the last video for chapter 14, I'm going to talk about Young's modulus and the shear modulus. And again, this is the rest of this material from chapter 14-4. Okay, so Young's modulus. So if you remember from the previous video, we looked at that graph that showed what happens, right? So if you increase the stress on an object, what happens to the strain, or this deformation graph called it. So remember, there was usually a linear part where the strain was directly proportional to the stress. So in that region, you can write an equation, right? So it's a line with the y-intercept of 0. So the stress on an object you can write as being some constant of proportionality times the strain. And this constant of proportionality y is called Young's modulus, or it's also sometimes called the elastic modulus. And in fact, some places use an e instead of a y for this. Okay, so, and unit-wise, well, remember, strain is dimensionless. Stress has units of newtons per square meter, so the Young's modulus is going to have units of newtons per square meter. And what it is, so it's a property of the material. So iron is going to have a different Young's modulus than steel, which will have a different Young's modulus than concrete, and so on. So it's independent of the size or shape of the material, so it only depends on what material you have. So, and another important thing to note, right, so there's differences between tensile stress and compressive stress. So depending on the material, you can have a different Young's modulus for tension than for compression. Okay, so you can do something similar for shear deformations. So this is kind of the picture. So imagine you have a box. So you apply some force that's in the plane of the upper surface here. So the box will get deformed. So, and again, basically you can define things, well, you can define it very similar to what we had for tension and compressive stresses. So here, we're going to define a shear stress. So we're going to use a Greek letter tau to stand for the shear stress. And again, this is going to be force divided by area. Right, the only difference for shear stress is that the force and the area are a little bit different, right, because the force is in the plane of the area here, whereas for the tension and compression, the force was perpendicular to the faces. Okay, so shear strain, so we're going to use a Greek letter gamma to stand for the shear strain. Again, it's a change in length over a length. The only difference is for shear, which lengths you're talking about is a little bit different. So here, the delta x, right, the way this is drawn is in the horizontal direction, whereas this height h is in the vertical direction. And again, remember, for tension and compression, they were in the same direction. So yeah, and I will also note that this textbook uses different letters, tau and gamma, for shear stress and shear strain. Some places will actually use the same sigma and epsilon that they used for tension and compression. Okay, so you do that, you can write, so there's an equation that's very, very similar to what we had for Young's modulus, and again, that the shear stress is directly proportional to the shear strain with this constant of proportionality we're going to call capital G, and capital G is the shear modulus. So again, it has SI units of newtons per square meter, and just similar to Young's modulus, it's a property of the material, and it's independent of the size or shape of the object you have. So in general, if you need to know what these Young's moduli or the shear moduli are, typically you look them up somewhere, or you go out and measure them. So this is actually a table 14.1 from your book. So, and you can look up, so for example, aluminum, right? So a Young's modulus is 73 times 10 to the 9th newtons per square meter, whereas shear modulus is 30 times 10 to the 9th newtons per square meter. Yeah, notice it's actually pretty common for most materials that the shear modulus is less than Young's modulus. And also for certain materials, especially things like bone, for example, Young's modulus can actually be different for tension and compression. Okay, and finally, so you can also look at the ultimate strength. So in this table, so this is the tensile strength and the compressive strength. Again, most materials are different in the maximum strength under tension and the maximum strength under compression. So this actually is the maximum stress that you can apply, and there's actually, so this table here, so this is a different well, this is from a different textbook, but it's the same information: tensile strength, compressive strength, and shear strength. Again, and it's actually pretty common, especially for things like wood, that the tensile strengths and the compressive strengths are actually quite different.